So actually, Abson, I contacted just generally a data science division in Swisscom, and they told me to contact with Abson to talk about Meerkat, their anomaly detection system, which I think is one of the most interesting systems right now used in any telecommunication networks. And you will hear why it's really interesting to talk about it. So Abson, she did like a master thesis a few years ago, and she was working on deforestation detection from satellite data using neural nets.
Oh, that was a very, very long time ago.
Yes, and after, as I understood, she did a second master thesis, and working on studying urban complaints on Twitter and popularity prediction on YouTube videos. And after this, she started to work on Swisscom, where she's already working for more than 5 years. And right now, she's a senior data scientist at Swisscom. So, please enjoy.
Thank you for the introduction. I see you did your homework. I'm happy to be here. Just to add, yeah, I did study here at EPFL. Yeah, I studied computer science, and I think the first class I attended was in this auditorium, or maybe CO2, but I don't remember very well. So it's a pleasure for me to be here. So today, as Pawel mentioned, I will present you Meerkat, which is the anomaly detection framework we developed at Swisscom. So first of all, maybe some of you wonder why we call it Meerkat, or what the heck a meerkat is. So basically, meerkat are these funny-looking animals always on the lookout. Whenever the sentry meerkat spots something suspicious, it will start to whistle, and everyone will run and hide. So they're pretty much the mammoth of the desert, so that's why we call it our project Meerkat. The team I'm working in at Swisscom is responsible for providing analytics for the core infrastructure of Swisscom. Our mission is to make sure that every services that is that we provide to you is running smoothly without disruption, and that you get the quality that you are paying for. So this is a little bit, how to say, a bad joke, but I guess for young generation, not having internet is something extremely, extremely bad. So why do we need anomaly detection at Swisscom? So I guess you can imagine that the Swisscom network is something very, very complex. And for the network engineer who has to take care of it, it's really not an easy task, because it is like immensely big, and there are changes happening several times a day. So we need to help them and automatize this anomaly detection, and by doing that, we hope to be able to not only extend like the coverage of the monitoring in terms of KPI, but also we hope to be able to do it 24 hours 7. Also, if we have automatized anomaly detection, we should be able to detect the problems we have in our network faster, and also resolve them faster. And then we can use the time that we save for our domain expert to detect, to solve the problem in the network, and basically to better use their time. So who can tell me where is the anomaly in this picture? Go ahead.
I'm just guessing that it was spiked in the middle.
Exactly. So I guess this example show you pretty well that if you use a static thresholding, there is no way that you could detect this anomaly. And I'm saying that because most of the tools we have out there, this is their approach, just putting a static threshold. I guess it's not a surprise for you guys that what we have to do is to use the historical data to learn the pattern of the time series, and use this information and compare it when we receive the actual measurement to see if it differs substantially from what we try to do basically is to compute a dynamic threshold, right, instead of using a static one. So with Meerkat, what we try to do is really to build a framework for anomaly detection. We don't want just to compare a bunch of algorithms, and the requirement we have for this framework is that it has to be real time, in the sense that we need to be able to alert the people whenever there is a problem within 1 minute. Also, we have to be careful to avoid alert fatigue. We don't want to spam people, right? Also, what we want to do is to provide contextual information about the outages or the alerts, such that people can take a decision quickly. Of course, this platform has to be generic and be able to handle different type of time series, and it has to scale into millions or billions time series, right? And the scaling requirement put pressure in other requirements that we have, especially the one that is avoid alert fatigue. So as of today, the Meerkat is a productive run product. It is used already by a few teams. Our early adopters are the people who are taking care of the mobile network of Swisscom. There are also a few people that look at L2, L3 telemetry data. So these are really low-level network statistics about Swisscom Cloud, TV, and voice over IP. And we are also using Meerkat to monitor the data that we are ingesting into our big data cluster, not network, and also the different processing pipeline that is running there. So this is the architecture of Meerkat. Let me just. So every time series we are monitoring Meerkat is fully described by a set of configuration that will tell how to query the time series, what model to build, how to alert, who to alert, etc. So the first building block of Meerkat is the data source client that will query the target data source. As you can see from this picture, we have drivers to different data sources. We have driver to Kafka, which is basically a distributed messaging system. We have driver to Drid, which is also a distributed time series database that allows to do very fast query metrics aggregation over multiple dimensions. We also have driver to Prometheus, which is the system we use for monitoring all the services and jobs running in our big data cluster. And once the data source client creates the data, it will send all the data to anomaly detection module that will take care of building the model, and upon reception of a new data point, it will give a score to this data point and pass it over to the outage building. The reason we have this second level of abstraction is that we don't actually want to alert on every small perturbation of the time series, right? We only want to alert on anomalies that are real problems. So once the outage builder has done its work, it passes over to the context enrichment layer, which basically will again query external sources and provide contextual information to this outage, such that people can know what is the likely reason of the outage and what is the impact, basically. Then this is passed over to the serving layer that will, on the one hand, build alerts and send it, and also provide all this data via a web UI, so people can have a look at the past anomalies and try to troubleshoot. So before I walk you through the algorithm we have experimented with, let me explain you how we did the algorithm evaluation. So we did on the one hand evaluate the algorithm on real data that we manually label. The shortcoming of this approach is that the outages in our network are pretty rare, so we didn't have a lot of label. So what we also tried to do is to generate synthetic data, but we did it in the way that it resembles real data. If you look at this graph here, you have a time series, and you see very well that there is a trend component, so the time series is increasing, a weekly cycle, so a period after which the time series repeats itself somehow, and a daily cycle. And one of the methods we use to generate the synthetic data is just using a sin function that we transform a little bit to have all these characteristics. Then we injected some white noise for every data point we generated, and also we injected at random position anomalies. Then we evaluated the different algorithms by varying the ratio of anomaly to noise to see how robust they were. This is an example of synthetic data we generated. So the first algorithm I would like to talk about is bucket algorithm. It's an algorithm that we developed in-house. It's called like this because what the algorithm does is basically it divides the time into small intervals, non-overlapping intervals, and it will assign each data point into a bucket based on its timestamp. So basically, for instance, we will put in the same bucket all the data points that are between 11 and 11:10. To illustrate this, for instance, all the data points that will fall into the green stripe will go into the same bucket. Then we will remove the weekly trend from the data. And the reason why we do this time segregation and trend removal is that we try to get a distribution that is stationary in a bucket. To estimate the trend of the time series, we simply do a linear regression over the n past the n weekly median, and the time series predictor is basically just the median of the bucket time the trend factors, and the data point will be classified as outlier if the difference to the prediction is bigger than some threshold time MAD. So MAD mean absolute deviation. It's basically a robust estimator of the scale of your distribution. Another model we experimented with is ARMA. For anyone who already play around with time series, he probably encountered ARMA. ARMA stands for autoregressive moving average. It's a very simple model that actually use the past P prediction to autogress itself and the past Q error to try to correct its prediction. Again, very likely as the bucket model, we will classify a data point as outlier if the difference between the prediction and the real value divided by the standard deviation of the past error is bigger than some threshold. We also experimented with the Twitter algorithm. The Twitter algorithm is an improvement upon the STL procedures. So STL stands for seasonal trend decomposition procedure based on loss. As the name suggests, what this method tries to do is to extract from the base time series the seasonal trend and residual components. You have an example of applying Twitter algorithm here. And then to detect the outlier, we apply a statistical test called generalized ESD test. Roughly speaking, this test, what it tries to do is it will take the likely outliers out of a base distribution and then compute the distance of those layers to the remaining clean distribution. And if the distance is bigger than some critical value that depends on the significant level that you want to have, then it will classify those data points as outlier. We also tried Kalman Filter. So Kalman Filter is a state space model. State space model, the general idea basically is to say that an observation is the result of a dynamic system in a given state. So our work is to provide these two metrics. So the observation transition metrics, which will tell how to transition from a hidden state to the observation, and a state transition matrix here, A, how to transition from the previous state to the current state. If you try to picture yourself a time series as being the trajectory of a moving particle, then you could use the position of the particle to estimate the value of the time series. And to infer where the particle will be next, then you can use its speed and position, right? And assuming constant speed, to simplify a little bit the problem, we have already worked out our A matrix and H matrix. Then we can use the Kalman filter to estimate the hidden state, and the Kalman filter will perform this in two steps. It will first do a priori estimation of the hidden state, and then it will try to correct this estimation by taking into account the state estimation error and the measurement error. We also experimented with LSTM RNN. RNN stands for Recurrent Neural Network. It's called recurrent because, as you can see on the top here, there is a recurrent link to itself. This recurrent link adds somehow memory capability to the neural network. And this memory is very helpful to model sequential data, because as you can see from the picture, when you want to predict an output, you will use as input not only the current data point, but also the previous one. The shortcoming of this model is that it cannot model like sequences, capture dependencies in sequences like long-term dependencies, basically. That's why the LSTM model was invented. It's pretty much the same thing than RNN. The only difference is that the hidden state is much more complex. It is this green box that you see here. I don't have time to go into detail, but basically the idea of LSTM is that it will use gates to decide at each step what to remember, what to forget, how much input it should let through, and how much output you want to emit. So we also experimented with different network architecture, trying different optimization function, activation function, etc., and it worked pretty well. Here you have an example of, in red, the real-time theory, and in blue, the prediction using LSTM. Our only concern with this model is that it takes really a lot of data to train. We had to use like between 7 to 10 months of data to train a quite simple model with, I think, only 2 layers. And this wasn't a realistic setting for us. It's way too much data. And also, back then, we didn't have access to GPU. So the training was extremely slow. Just to try it out one experiment, it took us between 20 to 30 hours. Our compute node wasn't that powerful, but still, it really limits what you can do. So bottom line, we compare all these algorithms using ROC curve. Here you have an example for Kalman and Bucket, and on synthetic data, Bucket was performing as well as all the others, but on real data, it was performing better, and our explanation is that it was much more robust to anomalies or outliers in the training data, and that it was also doing a better job at the inflection point of the time series. this is what I would like to share with you. The learning that I had while working on Meerkat is that, I mean, I'm working in the industrial settings, right? And if you want people to use the output of your model, they must be able to trust it. And to trust a model, you have to watch out for the quality of your input data. Even if you are not responsible for this data, in the end, if your model is only as good as your input that you have. Also, the model, if it is intuitive and easy to understand, people are more likely to trust your model and to use it because they can reason why you are producing such or such value. And I guess none of us like buggy and unstable software, and it's the same when you embed a model into a software. If it crashes all the time, people will not rely on it to make decisions. I think to build a successful data product, you really need the right mix of skill between software engineering and data science. So for people who want to become data scientists or already are, I will tell them not to neglect their software and system skill, because at the end of the day, if you want to work in industry, you have to productionize your model, and this means writing code. For the software engineer, I would like to say that, okay, there's a lot of hype around data science. It's a cool thing, but I would like to say that software engineering skills is equally important. And then finally, I would like to say that if you ever have to develop a project, and this is generally true also for software project, start simple and then evolve. Talk to your customer, try to understand what their need really are, and validate your hypothesis with them. This is the only way to really solve the right problem. So that was it. I also would like to say that we are hiring in my team and in Demoring team. We had a lot of open positions: data scientist, software developer, also big data engineer, big data DevOps engineer. All the job offers are online, but you can also talk to me directly. We're also looking for interns. I'm still waiting for the confirmation that we have the budget, but I'm quite confident that we will have. And I have to add that this project was initially started by a master's student who did an internship with us. So if you want to work on the next Meerkat, please contact me. Thank you. Oh, I can leave it in case of questions.
Actually, maybe start with one question.
Please.
So you talked about anomalies, but what actually is a practical example of anomaly? What do you constitute? What does this anomaly actually define as? Like it's an anomalous spike in the network traffic? Or?
So we have these two notions. So what I call anomaly and outage. Anomaly is anything, you can call it a statistical anomaly. So it's anything that is an outlier in terms of statistic. So even a small spikes. That's why we have this notion of outages, because we don't really want to alert on every small of these spikes. So basically, we built outages based on anomaly using a set of rules. I didn't really explain it here.
But it's going to be anomalous like activity of your devices, physical devices, or is anomalous movement in traffic in the network, or anomalous software which is moving? In which instances you can use Meerkat for?
Oh, it's generic. So we use it in various use cases to monitor very low-level network stuff, but also to monitor high-level KPI that you compute. It can be pretty much anything.
Mm-hmm. So you have different versions?
No. It's the same. It's the same platform. It's the same set of algorithm, but it's highly customizable. So depending on your need, you can get what you want.
Is this going to be only like Swisscom like private thing, or do you plan to maybe make it like public product or like open source?
I mean, you have seen the algorithm we used. It's public things, right? You can look it up. Then everything is running in premise in our platform. So right now there is no plan to outsource this, but we could maybe one day. But it's true that right now there's no such a plan. We didn't even think about it. Yes.
So you, at a certain point, you also mentioned the RNN solution. Did you actually test it and compare it with the other solutions? I don't remember on the slide if it was present.
So yes and no. We tested it, but we decided in the end not to use it because it required way too much training data. Most of the time we don't have that much historical data, and it was too slow for the hardware we had back then. But what I can, and also to be fair with the algorithm, we couldn't really push it to get the best ever result because the training was taking so much time we had to stop. But from the result we get after a few trials, it was quite okay. So I think it's a good model if you have the computational power to and enough data. Yes?
Thanks for the presentation. Did you also try or looking into maybe some unsupervised ways of, because I understand you have to make synthetic data in order to have, like a supervised test or enabled test, data set for testing and training and so on and so forth. Are you looking also into like unsupervised methods for, I don't know, it comes to mind like autoencoder, for instance,
Yeah.
it is used for anomaly detection in unsupervised settings.
Actually, the synthetic data we just generated to be able to evaluate those different algorithms. But when they're running in production, it's fully unsupervised. We don't have label, and that's also make the thing hard because we don't have label, and it's very costly to have. So, yeah.
Actually, may have one more question. How large is the problem when you have lots of devices in different versions, different time, in different software? How does it influence your system?
I'm not sure to get the question.
Let's say you are running thousands of servers in Swisscom, and you're detecting some anomalies in behavior, but you're not able to really control what kind of software and version and type of each of these devices is, and you are not able to make it uniform because it will be too expensive. So is it making some problems? Like that one device is faster.
Yes, it does. And actually, Meerkat helped detecting such things like this. So when we detect, for instance, that a group of customer, let's say, have, I don't know, experienced bad quality in terms of voice or in terms of whatever service they are using, then we try to find out who they are, and one explanation is that maybe it's some people using some devices with some version, etc. So Meerkat also, this is the contextual enrichment part I was talking about. So once we have detected that some people have experienced bad quality calling, for instance, then we try to nail down and figure out, okay, who are they, or yeah, things like this. But again, this I didn't explain. It would be too long.
Oh, any more questions?
Can you detect changes in seasonality as you
You could, but to be fair, is not something we do yet, because the problem is nobody really knows what to do when there is a change in seasonality. It can be to different reasons, but most of the time people struggle to really know if it's something you should detect or not. Like most obvious example is when people go on holiday and things like this, it will impact a little bit the time series, but some people will say, I want to detect it, and some others no. So until we reach some kind of agreement, we prefer not to solve the problem, let's say. But it's something we will have to tackle sooner or later. But it's definitely possible.
Is it possible now with Meerkat?
No.
Because you remove the seasonality in the signal before you do the analysis.
Right. Some algorithm does that, yeah. Okay.
Yeah, I was wondering the root cause analysis. I guess it's manual, or can you do this also to some extent a little bit more automatic? Because you have something which fails here, then as a consequence of different things.
No, everything is automatized. It's and that's the goal. And like when we generate an alert, all this information we would like to include in the alert. So when people receive it, they see immediately, oh, okay, this explains the anomaly. So, and then they can say, go and change something or do nothing or whatever. Yeah. Yes.
So I can use Meerkat to detect like anomalies due to, I don't know, cyber attacks, because there is a lot of, it's a hot topic now. Cyber attacks to detect, because they are classified as anomalies. So since it's a big topic now.
I would say yes. Actually, we detected one by accident. after it wasn't on purpose, but we detected something on this telemetry thing, data. We detected that something was weird, and when they looked up what was the reason, then they found out that it was an attack. But we didn't do it on purpose.
I will propose the last question, and after this we can move and drink some good wine.
Yes.
I have a question about who's the user of your model or tool. Is it always your group or team, or you just provide the tool to any department in the Swisscom that has this type of data and they use it, or you just give you the data and deal with it?
So the goal is to make it a platform. So anyone who has anomaly detection needs could use it. Right now it is at an early stage, so the data has to be in our big data cluster. If it's there, then it's really easy to use it. But our approach is that you shouldn't be a statistician or a machine learning expert to be able to use it, right? So it should be very easy. Of course, if you have a deep understanding, then it's better for you. But yeah, it's for everyone. It's really for everyone. Most of the network engineers we work with, they have no background in statistics at all. That's why the model has to be intuitive, because otherwise they're very suspicious. They're like, what is this? Why are you providing me this information? And things like this.
So, thank you very much.
Thank you.